Okay, so I feel compelled to um, make a video uh, about Helion. So I'm recording my screen so that I can show you their animation on their website in the technology section. So this is going to show us their reactor, which is not a tokamak. Um, if you ever work out with dumbbells, you could like consider it, instead of like a donut shaped tokamak, it's kind of like a dumbbell, uh, where field reverse configurations are generated at either end of the dumbbell, and the thin central part is where fusion occurs. But anyway, so um, uh, uh, so anyway, notably the fuel for this is deuterium and helium-3. And so deuterium is simply an isotope of hydrogen, which is extremely abundant on Earth. Um, and so there's enough deuterium uh, in all the water sources on the Earth to power this kind of reactor for like the order of billions of years. The constraining thing is actually helium-3, um, which is in limited supply on Earth, but interestingly is abundant on the moon. And so, with partnership from SpaceX, right, which is going to be going to the moon, the United States can mine helium-3 from the moon, both for fuel for this fusion reactor and also as a cooling agent for quantum computing, because to do quantum computing, you need uh, a temperature, close to 0 Kelvin, um, because the temperature is sort of like, so to speak, noise that can interfere with the quantum state in the computer, like a superposition state, entanglement, and so on. All that is possible under certain minimal temperature noise. So, but anyway, that's a tangent. We're talking about fusion, and so the magnets confine the helium-3 deuterium combination plasma into a field reverse configuration, which looks like a ring. And then they accelerate that, um, and then they collide in the center. Um, uh, and so then a magnetic field compresses the field reverse configurations. Um, and so um, um, basically, the compression of the FRCs increases the temperature, and that's how it gets it to fusion relevant temperatures. Um, and ultimately, then there's the fusion. Um, uh, so the whole that's critical here is that energy is required in terms of the magnetic field that accelerates the field reverse configurations and then compresses the plasma in the center. But upon fusion, more energy is released from fusion than the energy required to start the fusion. Um, and so when fusion occurs, then the plasma expands because it's the sun is a fusion reactor, and so it's a consistent expanding explosion. But what's keeping it confined is the mass of the sun. So, it's constantly, fusion is happening constantly, um, uh, you know, at the center of the sun, with four hydrogens forming two deuteriums forming a single helium. Um, um, but the mass of the sun is what's constraining that explosion into a approximately perfect sphere. Um, anyway, um, and so the plasma expands, um, and so um, the whole thing is that the next slide, the critical thing is how are they generating clean electricity with this process? And so that's just direct electricity recapture. Um, uh, yeah. Uh, so the whole idea is that if the magnets at the center are sort of compressing the plasma to start fusion. And so when the plasma expands, it's pushing back on those magnets that are trying to compress it, right? And then there are also the magnets that are, accelerating the plasma from either end towards the center. And so if that expansion includes the plasma uh, moving horizontally or expanding horizontally, it's pushing back on the magnetic field designed to accelerate the plasma towards the center as well. And so when it pushes back on that magnetic field, it causes a change in magnetic flux. And so, from Faraday's law of induction, that induced electromotive force is the negative rate of change of magnetic flux. And so if the plasma is pushing back on magnets that are designed to constrain the plasma, that is directly generating electricity, and that electricity from the resulting fusion is directly recaptured. Um, and so that's their system. Um, and so, I just thought it would be cool to spread awareness about it. And so this company is building the world's first fusion power plant in Washington. And so they have a contract with Microsoft to provide clean fusion electricity to Microsoft data centers by 2028. And they are, in my understanding, the only fusion company that has such an aggressive timeline for that. So they're actively building the world's first fusion power plant in Washington, United States. And so the other thing I want to point out about their approach, I'm going to ask Grok. So let's say um, uh, 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 why is helium-3 deuterium fusion a good idea? So I'm going to wait for Grok's answer. I, of course, already have an answer, but for the purpose, I'll just wait to see what the model says. So, and this is another thing. So, Grok 4 Heavy is nearly pretty much PhD level at almost every subject. Um, and so, um, the world's best language models are better software engineers than the majority of people with undergrad degrees in computer science. GitHub Copilot can read your whole code workspace, and with natural language prompts, basically solve almost all the problems in your code workspace for you and make nuanced code modifications. Um, and so that's one of the reasons I'm going into masters in electrical engineering, because um, you know the software space is getting disrupted by LLMs, whereas electrical engineers who need to like utilize uh, software to do um, circuit design and CAD software for electronic component design, and obviously as well hands-on electrical engineering. The AI movement is not really close to automating electrical engineers away, but computer scientists, yes. And so the only computer scientists will be the people who can build, train, and deploy a large language model product. And so by build, I mean build the neural network architecture, build the self-attention mechanism, right? And train it on the data on the internet, and deploy it to like some endpoint on the internet. So Grok is deployed to a web endpoint that users can access, right? Um, um, and so I foresee that LLMs will replace majority of entry-level software engineers. So the only computer scientists will be the people building, training, and deploying LLM products themselves. And then the electrical engineers, because they again need to do hands-on engineering and CAD work, designing electrical schematics and this, that, and the other, are not as readily going to be replaced by AI systems and LLMs. And so as an electrical engineer with a master's, it would be epic if I could work as a Helion energy electrical engineer, working on magnetic confinement or magnetic acceleration or direct electricity recapture for their fusion reactor. A computer scientist could not do that job. And then the LLMs will be quicker and better than majority of so-called computer scientists with bachelor degrees. And then the only computer scientists will be the people building the LLMs themselves. That's the future. So, hey, if you want to be a computer scientist, the only thing you should study is how to build, train, and deploy an LLM. Because you could consider a human brain as a neural net. It can read so many computer science textbooks. It can read all the code examples on the internet. LLM does that with infinite more capacity than a human brain, right? With more parameters, and it's just better than you. So majority of people do Geeks for Geeks coding contest on the world's best LLM's best attempt. It will outperform the majority of humans, even if the questions are originally written. So I'm doing electrical engineering, but I still know how to code. I know some Python and some C and some full stack engineering principles, but I'm passionate about physics and electrical engineering and hands-on engineering, and making engineering projects that are not just abstract software, but some epic large-scale physical engineering project like an autonomous car, a SpaceX rocket, a Helion energy fusion reactor, all these things fall under the branch of electrical engineering, mechanical engineering, and computer science is, more abstractly going to like operating systems, mobile and web app development, AI, algorithms. Anyway, so let's see what this thing is saying. Um, I'm gonna read this entire response. Helium-3 deuterium fusion involves fusing a deuterium nucleus, one proton and one neutron, with a helium-3 nucleus, which is two protons and one neutron, to produce helium-4, a proton and a significant amount of energy. I would say 18.35 mega electron volts per reaction, okay? It's considered a promising approach to nuclear fusion compared to more conventional deuterium-tritium or deuterium-deuterium fusion. And so aneutronic nature, that means it does not produce any neutrons. Okay. Few or no neutrons as direct byproducts. So it releases charged particles like protons and alpha particles, which are helium-4 nuclei. So neutrons from deuterium-tritium fusion, which carry about 80% of the energy, okay, can activate reactor materials, making them radioactive. You need to do shielding and generating long-lived nuclear waste. And so with deuterium helium-3 fusion, there's pretty much no nuclear waste. And so what Helion thought through is that their reactor doesn't even produce radioactive waste with use of deuterium helium-3 fusion. So potential for direct and efficient energy conversion. The charged particles produced allow for direct conversion of kinetic energy into electricity using electromagnetic fields, bypassing inefficient thermal cycle. And so Helion's website says that their direct electricity recapture allows the reactor to skip the steam cycle. This is what they're talking about. And so the whole idea, okay, it could achieve conversion efficiencies up to 70%, far higher than traditional methods, making the overall system more compact and cost effective. And so if you recall, they said that the energy released from fusion is more than the energy required to start the fusion reaction, which is the magnetic fields that accelerate the FRCs towards the center and the magnetic field that compresses the plasma in the center. The energy released from fusion is more than the energy required to start fusion. And so if you're capturing 70% of that energy released, you could still have a thing where obviously the energy directly recaptured is more than the energy required to start the fusion. And so this doesn't violate conservation of energy. It's just exploiting fusion such that, okay, requires energy to accelerate the plasma towards the center, compress the plasma in the center. The energy released from fusion is more than the energy required to start the fusion. A high percentage of that energy released from fusion can be directly recaptured as electricity. And so ultimately, you get more electricity coming out of the reactor than went in, ultimately, mathematically. Uh, and so, anyway. Um, anyway. Um, so, yeah. Higher energy output per reaction. So, deuterium fusion releases 3 to 4 mega electron volt per reaction. Deuterium helium 3 is 18.35 is 18.35. Yeah. So yeah. Abundant and clean fuel sources. So deuterium is readily extractable from seawater in vast quantities. Helium-3 is rare on Earth, abundant on the lunar surface, which I had previously said, so it's deposited by solar wind. It's going to be mined from the moon, and so SpaceX will, be critical in lunar mining of helium-3 for both this fusion reactor and then also as a cooling agent for quantum computers. Anyway, this fusion process produces no air or water pollution, no greenhouse gases, and no proliferation risks from fuel breeding, unlike deuterium-tritium, which requires tritium production. And so it's positioned as a low-carbon, sustainable energy source that could help mitigate global warming, yeah. So, okay, last section. Lower overall costs and simpler design. Okay, without the complexities of neutron management. Hold on. See, okay. Lower overall costs and simpler design. So, without the complexities of neutron management, deuterium helium-3 reactors could have lower capital and operating costs, smaller sizes, and reduce technical challenges compared to neutron producing fusion systems. Yeah. So, makes it potentially more feasible for commercial deployment. Okay. Yeah, so the helium-3 sourcing will have to be established with lunar mining. So it says while deuterium helium-3 fusion requires higher temperatures to ignite due to stronger electrostatic repulsion and faces challenges like helium-3 scarcity on Earth, its benefits in safety, efficiency, and cleanliness make it an attractive second generation fusion option. With advancements in lunar resource utilization. So we're going towards a future in which SpaceX will provide lunar mining of helium-3. Helium-3 will be used as fuel for this kind of fusion reactor. Helium-3 will be used as a cooling agent for quantum computers. So anyway, I'll close with doing the reverse process of this animation of the reactor. Right. Okay. Cool. So this has been my overview of Helion. Um, 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 if you are an accredited investor, I would urge you to go ahead and invest in Helion. It is not a publicly traded company. So, but they are the only company with it as aggressive of a timeline of 2028 to produce clean fusion electricity to Microsoft data centers. And they are actively building their world's first fusion power plant in the state of Washington. So, um, um, subscribe to the channel.